Okay, so now we're going to get into two-variable quantitative data. We just did categorical, now we're going to do quantitative. So, in this presentation, you're going to learn how to identify explanatory and response variables, how to make a scatter plot, describe the direction, the form, the strength, and relationship between two quantitative variables, interpret correlation, understand what correlation is and how it is influenced by outliers. We might actually not get to that one. Use technology to calculate correlation, and then explain the difference between correlation and causation. That is probably going to be, well, I'll figure it out. All right, so what is the difference between an explanatory and a response variable? So when we say an explanatory variable, we're talking about what is traditionally the x variable, right? It's the horizontal axis variable. It's going to help us explain or influence, it may help explain or influence changes in a response variable, and we are going to put it on the horizontal axis, right? So it is the variable that we are arguing has an effect on a different variable. The response variable is the outcome variable. It measures the outcome of whatever study we're referencing, right? We're going to put that on the vertical axis. It's what's going to be traditionally known as the y variable, right? So you have x and you have y. X, we're assuming, is what makes the impact, and y is the result of whatever x does, right? Now, in algebra classes, we often see linear relationships. You have an x and a y that change directly in relation to each other. In reality, that's not how things normally work. You have relationships that follow certain patterns but don't necessarily follow a strict line, right? A scatter plot is a representation of two quantitative variables, statistics. They show a relationship between two quantitative variables. Each individual data point appears on a graph, and it represents both a value on an x and a corresponding value on a y axis. And they're described by finding patterns. We look for things like the direction, the form, and the strength. And again, if we see any outliers, just like in Unit 1, we have to make note of any outliers. When we're describing scatter plots, we look for a few things. One of the first ones is we look for an association, right? They can have either a positive or a negative association. If it slopes downwards, if as we go from left to right, the scatter plot is going down, then we say that is a negative association. If the scatter plot is increasing as we go from left to right, if it drifts up, then we say that is a positive association. This scatter plot picture has a roughly negative association. It starts off in the top left corner, and it ends up in the bottom right-hand corner. There's some zigzagging along the way, but for the most part, it follows a negative pattern. Strength. The strength of a scatter plot, or the strength of a relationship, describes how close together the points are, right? Points can be considered, the strength can be, or a scatter plot can be considered weak, moderately strong, can be considered strong if the points are very close together, can be considered moderately strong if they're slightly scattered about, and it can be considered weak if they're very scattered. I would say this scatter plot pictured here is relatively strong. We may consider this something moderately strong, but I would make the case that this is actually a strong relationship. Then we have the form, right? We're going to focus a lot on the linear patterns, but it is completely within the realm of possibility that you have a curved relationship, the form is curved. So if it's an exponential data set or if it's quadratic pattern following data set, it could be curved up or down. So that is something we will eventually get to. But for now, most of the time we'll have a linear form. So, example that we have here to the right. Describe the scatter plot. Well, I see that it goes from bottom left to top right, so I would make the argument that it is a positive relationship. I would say these points are relatively strong. They are relatively close together, so this is a strong relationship. And it's linear, right? It doesn't seem like it's curving up or down, so I would say this is a positive, strong, linear relationship, points per game and wins, which makes sense. It makes sense that in any sport, if you score more points in a game, right, And there you go. That is describing scatterplots. Now, there is a way to measure the strength of a scatterplot and the linear association, and that measurement is called the correlation. Correlation of an association measures the direction, the direction and the strength of a linear relationship between two quantitative variables. It's always going to be a number between -1 and 1. If it's a positive number, then it represents association. If it's a negative number, it represents a negative association. The further away it is from 0, the stronger the linear relationship is, right? So the closer it is to 1 or the closer it is to -1, it's going to be a strong relationship. So 0.9 is a really strong positive association. Negative 0.9 is a really strong negative association. If it's close to 0, so like 0.1 or -0.15, those are relatively weak associations. And here's some examples, right? Here we have a correlation of 0. This looks like there is no pattern. It's just a bunch of dots. You could make the argument that they're increasing just as much as you can make the argument that they are decreasing, randomly scattered. No pattern. Then we have something that is relatively weak. It is a weak negative association. The correlation coefficient is -0.3. Over here to the right, we have something that is moderately strong. This is that medium range. Correlation coefficient of 0.5. So it's positive. It's a moderately strong positive linear relationship. Over here, down here, we have -0.7. This is right on that line, right? I would say that -0.7 is right on the line of moderately strong and strong. You can make the case for this one either way. You may be more comfortable referring to this as moderately strong as opposed to strong. So you could refer to this as a moderately strong negative linear association. And then the last two are strong, and then over here we have very strong. So this is what it looks like if a correlation has a coefficient of 0.9. And over here, this is a correlation coefficient of -0.99, of course, it's going down, right? You very rarely, if ever, will see a correlation coefficient of 1 or -1. In order for that to happen, every point has to fall exactly on a line, which means it's probably not real data. You can get something that's very strong in the 0.9 and 0.99 range, but it is very rare that you'll see something with a correlation coefficient of -1 or +1, unless it's just either not enough points, like you can get it with 2 points, or if the data is just not very good, or made up data. You can make up a very strong relationship. Algebra, right? All right, so in order to calculate R, this is the formula that we're going to use. Please go ahead and write that down. I'll give you a second to write it down. We don't actually do that by hand. On the slides, there's a link to finding it in the calculator. It's almost always going to be given to us, but most scatterplot calculators and regression calculators give it to you. It's not something that we do by hand, ever. Like the standard deviation for Unit 1, we very rarely will do, we won't ever actually, I can't think of a single instance you've ever been asked to find R by hand. It's just something that you find in the calculator. You're either asked to approximate it by looking at the picture, or you're asked to find it in the calculator. Either one or the other. Never calculating it by hand. And then some things to keep in mind about correlation. First of all, correlation makes no distinction between explanatory and response variables. If you flip the x and the y and swap them out, you're going to have the exact same correlation coefficient. Just because on here, if I change whatever was on the x-axis and put it on the y-axis and put the y-axis on the x-axis, my relationship between the two is still going to remain the same. It's still going to be decreasing. It's still going to be very strong, and it's still going to be linear. R also isn't going to change when you change units. R has no units, so it wouldn't matter if you changed the units, right? If you changed one of your, even if it's only for one of the axes, right? If I changed from feet to inches, I'm still going to have the same R value. If I changed from shoe size in centimeters to American shoe sizes, again, it's not going to make it. Correlation doesn't describe curved relationships no matter how strong they are, right? So you're never ever going to use R to describe a curved relationship. You're only going to use R to describe a linear relationship. There are other metrics we use for curved relationships, and we'll get to those, but R will only describe linear relationships. Correlation is not resistant. R is very much affected by outliers, right? If I go back, I mean, you look at what correlation is in practice. The thing that makes R strong versus weak is how close the points are to each other. If I add 1 or 2 points that are outside of the range of the rest of them, that is going to significantly decrease my strength. They change my value for R. So, of course, R is very much affected by outliers. R itself is not a complete summary of 2 variable data, so just getting R is not going to tell us much. It'll tell us if things are strong, weak, or whatever, but it doesn't give us a y-intercept, it doesn't give us a slope of anything. It's just a measure of how tightly knit the points are and what direction they go in. And then always remember that just because there is a correlation between 2 values, that does not mean there is a causation. There is a way to test to get causation, but it is not done by finding R, right? No matter how strong R is, that will not tell you that there is a causation or a causal relationship between 2 variables. The only way to do that is through testing and specific survey methods, which we will get to. But it is not done by simply getting a really strong correlation. Strength of correlation does not force there to be. And there you go. That is intro to 2 variable quantitative statistics. Hope this was helpful.